Okay, so this is to the right, and then this is to the left. So one's bouncing off one wall and one's bouncing off the other wall, and they are messing with each other in between. And we know the expressions, and we can add them together because they add linearly, so we just have a nice summation there. And what do we have? We just have a difference in signs, and you remember this, don't you? Sine A plus or minus sine B equals that thing, so you do it, and you get the answer, y equals 2a sine kx cosine omega t. You don't have to know that equation, so don't commit that to memory. Again, I'm not above giving you that equation and saying, so do something with it, but you don't have to commit that to memory. What it does do, though, if you play with your graphing calculator, it gives you that pattern where it gives you a graph that looks like that. It's a sine curve, but it's modulated amplitude as it goes on. Standing wave is an oscillation pattern with stationary outline that results from superposition. Oh, I'm sorry, no, it's not. It's that pattern. Silly me. It's actually that. It goes like that. So what I drew was actually to do with beats. So we get that, and then there. So, and then it goes and says, oh, look, we have an equation for where, the nodes are, and we have an equation for where the antinodes are, and I hate it. Just draw the pattern. I'm not going to ask you to draw the pattern of the 17th harmonic. It's going to be 1, 2, 3, or 1, 3, and 5 on the open tube. It's going to be the patterns we've seen. So, yeah, you want to know this, but not for a test. It's like, it's just, I get sometimes I think that they get paid by the page, and they just say, let's just work this stuff out. So this is what's important. Yes, that is an allowed vibration mode because it's got a node at one end. Yes, and that's also allowed. But this is not allowed because that's an antinode right where a node should be. So there's a certain logic to this. So we go through the patterns and we go through the math which we just did. Basically, what's the length? Express the wavelength in terms of the length, and then go V equals F lambda. So F is equal to V over lambda, and you can figure out that this is if this is frequency 1 equals 100 hertz. Then frequency of the second harmonic, which is the second pattern, equals 200 hertz. And then the frequency of the third harmonic, which is the third pattern in this case, which equals 300 hertz. And so then we can have a question like a guitar string is fixed at both ends. It is 2 meters long. This is 2 meters. Transverse wave has a speed of 5 meters per second, so V is equal to 5 meters per second. Do you have this in your notes? No. Oh, I'm sorry. I'm sorry about that. So we'll just work through it. That's a bit worrying. So what is the wavelength of the first harmonic? So you'd say first harmonic looks like this. You'd say L is equal to lambda over 2. So lambda is equal to 2L, which equals 2 times 2, which equals 4 meters. Agreed? Yep. Agreed? And then what is the frequency of the first harmonic? Well, you'd say that F is equal to V over lambda, which equals, I was given my V. My V is 5 over my lambda, which is 4, which equals 1.25 hertz. Not a very big hertz, but there it is. And so the answer for that one is B. So a typical test question would be, draw me that. Draw me what it looks like. Then work out what the wavelength is. Then work out what the frequency is. I might, if I want to just cut time, just say, give me the frequency, but I want the diagram. I'll always want the diagram. Yeah. So not so bad, yeah? You got this picture? Okay. Yeah. So resonance. This is a little bit, it's funny that it's here. So resonance basically says, look, if I have an oscillator which is, well, an oscillator has a natural frequency. So a tube of air is a natural frequency. If I try to drive that natural frequency at a weird frequency that's not related to its natural frequency, I'm not going to get very far. I'm going to push when I should be pulling. I'm going to pull when I should be pushing. I'm going to cancel myself out. That energy is just going to dissipate as heat. But if I match the natural frequency of my oscillator to if I match my driving frequency to the natural frequency of the oscillator, then I will find that I push when I should push, and I pull when I should pull, and the energy stays in there. If you think about it, you're acting a bit like, it's an interesting point actually, you're acting a bit like a plunger at this antinode. And if you do what you should do at the same rate and at the same time as is expected, you're going to put more and more energy inside the system. We know this because when we go to the park, if we push our kid on the swing and we pay no attention to where they are, we'll just jerk them around. They won't go higher and higher. But if I always push when my child is on the downswing, if every time my child is on the downswing, I'm going to put more and more energy into it, and so my child's oscillations are going to get bigger and bigger and bigger. Yeah? So we kind of know this intuitively. Good things and bad things. You can make this work as a way of transmitting information. So you can have a transmitter, say a radio station, transmitting information on a carrier electromagnetic signal, which is at a certain driving frequency. And if you happen to tune your radio set to that same frequency, so now the natural frequency of your radio set matches your radio station's carrier frequency, then that sustains and you hear it. But if you tune your radio set to a different natural frequency, then your radio station will no longer be in sync. It'll be pushing and pulling at all the wrong times and you won't hear it. Or, for example, if you're in tune with this green radio station, if I have another radio station, say the red one, and the frequency is incorrect, I will not hear it on my radio. So it's not that your radio somehow doesn't pick up all the radio stations. It does. And it's not that your radio says, that's the wrong radio station, I'm going to reject it particularly. It just says, okay, I'll receive it all and amplify whatever I can, and I can only amplify the bit that's at my natural frequency. So cheap radio sets do that somewhat, and good radio sets have much more filtering in to do that much better. But that's the name of the game. There was a video, did I show you the video where they had the little cart going backwards and forwards? Yeah. And did I show you anything of the video with the bridge, where the bridge went? Oh, so I don't know if I can do it. I'm not going to play with it. I want to just get through this today. But online, on our website, there's a video of the Tacoma Narrows Bridge. And the Tacoma Narrows Bridge, they built a suspension bridge. A few months later, a whole gusty wind came. When you blow over something, it tends to flap because of fluid mechanics. The natural frequency of the flapping frequency happened to be the same as the natural frequency for the bridge. I mean, can you imagine the bad luck? And the energy just stayed inside. The oscillations got bigger and bigger, ripped the bridge apart. So a couple of months after this bridge was built, it fell apart. Can you imagine? People lost their jobs over that. Nobody lost their lives. A dog apparently died. But there's a picture of a guy walking away from his car. And he's like, it's probably that guy, but he's walking away from his car, and you can see behind him the bridge is going like that. And you know that car's not going to stay there for very long, you know. So it was a very lucky situation. And as a Boy Scout, you're taught break step when you go over a bridge. You know, chances are it's not going to happen, but you never know. If you ever take your child to Busch Gardens, if you go to what used to be the dinosaur land and now is the Elmo land, for the kids, they have these rope bridges. You're walking across with your 3-year-old. There's some middle school boy bouncing up and down in the middle of the bridge, hitting the natural frequency. And so the oscillations are getting higher and higher, and your kid's getting terrified. And if you're an ex-teacher, you tell them to stop doing that. And because you got that voice, they stop. It's the most amazing thing. My friend, so I was at a Bob Dylan concert 30 years ago. And it was an all-day affair. It was a whole bunch of headliners, and Bob Dylan was the final act. And he came out. There was Bob Dylan, Eric Clapton, and Eric Clapton was the act before Bob Dylan. And Bob Dylan said, "Eric Clapton's here," like we didn't know. And I'd like to invite him to play with us. And Eric Clapton kind of comes out, like all bashful, because he's been invited on the stage with Bob Dylan. Because at the time, Bob Dylan was huge, and Eric Clapton was huge in England, kind of thing, And everybody gets excited, so everybody stands up, and it's like I think in that one there was 500,000 people or 250,000 people. It was huge, and they're all standing up, and you sat there, and you're thinking, "Oh no, oh no, oh no." So, "Oh no, I'm sorry, guys." They're standing up from the back, and you can hear it. Kind of people are standing up, and you're going, "Oh, I hope we don't have to stand up." And people next to you stand up, and then, "Oh no." So then we stand up, and people in front of us stand up, but then it just stops. There's like 3 rows in front of us standing up. We're just on a field, and my friend Elaine, who was a high school teacher, there are all these bikers, leather jackets and everything, and she goes, "Sit down," and they all sat down. So we had this beautiful view. She just that voice. So anyway, develop the voice, and life will go much better. And don't bounce around on rope bridges, because it'll drive people crazy. So here's the problem. When you try and do the compressions and rarefactions, and I'm drawing it as a compression here and a rarefaction there, and I'm not sure I should, but, it's a visualization. And then how would I prefer to draw it? Well, I could draw it like this. This is the one that's open at one end and closed at the other, and this one's the one that's open at both ends. The one that's open at both ends is just like a guitar string in reverse. Where there was a node, there's an antinode, or where there was an antinode, there's a node. But this is a different kettle of fish. Yeah. So watch out for that. And the skill is, can you draw the diagram? Can you work out what the wavelength is? Can you work out what the frequency is if I give you the numbers? So an organ pipe is open at both ends. The organ pipe is 5 meters long. Assume the speed is that. So here's the organ pipe. It's 5 meters long. And V equals 330 meters per second. That's about right, actually. And then second harmonic. Yes, we do have a second harmonic, don't we? So you can just cheat it, and you can go, there's my first, and then my second will be that. Yep. So I go. Did I do that right? Yes. There's my second harmonic. That's my first harmonic. That's the simplest pattern. This is the next more complicated pattern, so it should be the second. And then what I do is I say, what is the frequency of this second harmonic? So I say, what's the wavelength? L is equal to lambda. So lambda is equal to L, which equals 5 meters. And then what is my frequency? F is equal to V over lambda, which equals, in this case, 330 over 5 meters, which equals 66, I think. Is that right? 66 hertz. So my answer's there. So not so bad. You've got to know the pattern. You put those two things in nice circles so I can find them, or boxes, and I'm a happy camper. Next. Organ pipe is open at one end and closed at the other. 6 meters long. What is the wavelength of this third harmonic? So my first is that. And my second pattern is that. And this is a little alarm bell is going off, because I remember this from class. That's my third harmonic. So there's a little bit of memorization there. You got to attend and pay attention. And so I say, well, my wavelength, my L, is equal to 3 over 4 lambda. Is that right? There's a quarter, there's 2 quarters, there's 3 quarters. So that means that my wavelength is equal to 4 over 3L, which equals 4 over 3 times 6, which equals 8 meters. So there's my first answer. And then what is my frequency? Frequency is equal to V over lambda, which equals V, which is 300, over lambda, which is 8, which is 3/8 of 24. Is it what? 37.5. So then C is my answer. Yeah? So not bad. A little bit of conceptual stuff there, isn't there? If you didn't know there was if you didn't know that second pattern was your third harmonic, you get it wrong. So. Can an organ pipe that's open at both ends have a second harmonic? Yes. Who thinks that? Oh, well, vote. So vote. Yeah, just click now. It's open. Click, click, click. 4 people have voted. 5 have voted. 6 have voted. Come on. How many is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17. 17. I got 12 people voting. 17. I got 13 people voting. Can I get 15, 16, and 17? Oh, come on. Come on. Not working? There's 15. 2 more people. What the? Oh, 1 more person. Come on. Come on. Yes. Okay, so then let's stop it. So you can't change your decision. And now let's have a look at what the... So mainly A, a little bit of B, a smidgen of C. So let's look at the question. Can I move this? Yeah. So can an organ pipe that is open at both ends have a second harmonic? Well, my simplest pattern is that. And my next simplest pattern is that. And if I work out my frequencies, it's twice. If you think about it, it's half the wavelength. This is lambda over 2, and this is lambda, so it's half the wavelength. So it scales. So can I have a second harmonic? Oh yes, I can. It's not that one I need to worry about. It's the organ pipe that's open at one end and closed at the other. That's the odd one out. So let's close you off. Let's go here. And beats. Oh, this is like, I love this bit. So I want to show you something. This is a really good day for me because I'm using the new technology. I'm using the new technology. I'm using the clickers, and I'm doing demonstrations. I mean, this is like, you know, I should be in the Hall of Fame of physics instructors. So this is a tuning fork. It's an instrument that's designed to give us only a modest, mainly the fundamental, mainly the first harmonic, and very little of anything else. As they get dinged up, you get higher and higher frequencies coming in, which are higher harmonics. So when you buy them, you like to keep them kind of nice. So we don't hit them with hammers and stuff. We use these little rubber things. And if we want to make them sound louder because of the, so the class can hear, we put them in an amplifying box, like a guitar string. This is a crack in it. Oh, that's not good. That's why it zings, I think. Okay. So that's like a guitar body, making the sound more. Boom, 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 boom. Okay, so there's the sound. About the extra mass. Here's make a difference. Watch what happens when I... There's a change, not in the pitch, there's a change in the loudness, and that is beats. So a beat frequency is the frequency of the modulation of the loudness. It's not the change of pitch. The pitch you hear is the average of these two. So you tend to notice this when the frequencies are quite similar, because if I change this by too much, then the beat frequency is so high I can't detect it when I'm listening. It just is like another hum that I'm not noticing. So it's only when, so if I make this one just slightly less, I should slow down the beat frequency. This is not a linear scale, I'll tell you that much. And if I do this, and as I go to a high frequency, so that's the game we're going to play. The two things I need you to know: how do you work out the carrier frequency, that's the pitch that you hear, and how do you work out the beat frequency? I can use a visual analog. Here are two patterns that have a certain frequency in space. I could talk about their wave number, couldn't I? Rather than talking about their frequency, which is cycles per second, yes? I could talk about their wave number, which is cycles per meter. So this is very good, actually. So, and they look somewhat similar. You can kind of tell they're lining up here, they're not lining up there. I should do that on the thing, shouldn't I? You can kind of tell, you know, they're lining up at, you know, they're lining up there and there and there and there, and they're not lining up at the other places. So these guys will cancel and these guys will add. But you really notice it down here, don't you? You can kind of see that, you know, there's nodes and anti-nodes, or constructive and destructive interference. Where's the math? You're not responsible for this math, but there's one wave and there's another wave, slightly different frequencies. We do a bit of a trigonometric identity, and yada yada yada. And we get these two answers. The sound is carried by a beat frequency. You need to know that. This is the carrier frequency, F carrier. What carries the sound? F carrier. And then what's the beat frequency? This is F beat. You need to know those. This one at the bottom is the envelope. And this is the one where it actually... So this is the one where it has like the envelope to it of loudness.
So,
Okay? Yeah.
So the carrier frequency is really just an average of the two frequencies?
That's exactly. It's just an average of the two frequencies.
Okay, that makes sense.
And the beat frequency is the difference, but you don't worry about the sign.
Yeah, because it's...
Doesn't matter. It's just which one you decided to put first. Yeah. So there it is. That's that. And then last little thing is on... Oh, so... pure tone of 1260 hertz, and a pure tone means single frequency, of 1258 hertz sound together. What's the beat frequency? So F beat is equal to 1260 minus 1258. Putting absolute signs everywhere. So that's going to be 2 hertz. And F carrier is equal to 1260 plus 1258 over 2, which equals, I don't know, 1259. Every semester, somebody gets them backwards because they don't remember them. They just go, oh, one of them's the average and one of them's the difference, and that's not right. You got to know what carrier means, and you got to know what beat frequency means. Yes.
So the
So it gets louder twice a second because the hertz is per second.
Okay.
So 2 times a second it gets louder, 2 times a second it gets softer.
So it changes 4 times or whatever.
There's 2 ups and 2 downs, yeah, so however you want to do it. But yeah, you can interpret it as, I mean, the simplest way is to say the hertz is the number of times it gets loud per second. Yeah, good. So this is, now we're on to the last little thing, sound quality. So if I'm playing my piano and I play 512, and you're playing your guitar and you play 512, they sound nice together, agreed? But I can tell them apart. What's the difference? What is the difference? They're playing the same frequency. If I was to take yellow paint from one pot and yellow paint from another pot and mix them together, I couldn't tell them apart. But I can take 512 from one instrument and 512 from another instrument and tell them apart. Not only that, I can get the cheapest transistor radio going, just a little cup with a little capacitor connected kind of thing. And I can still hear well enough that I can tell that there's 2 instruments. I can even tell you what the instruments are. In fact, what's even really weird is that I can play you an instrument you've never heard before. And I can play you 2 instruments that you've never heard before. And I believe you can tell them apart. But if I was to try to do the same visually, I couldn't do it. And so it's a very weird system. So why does a 512 playing piano sound different from a 512 playing guitar? And it's not because they have different frequencies, because they're both playing 512. But what they've got is different harmonic magnitudes. So, you know, the piano might be a big first harmonic and a smaller second and a smaller third and then a bigger fourth and a bigger fifth, whereas the guitar could be a relatively small first harmonic and a bigger second and a smaller third and fourth. So the frequencies are all identical, but they are different patterns. And so they sound harmonious, but they sound interestingly different. And that's the wonder of it. That's why there's not many orchestras or bands made up which play tuning forks. It's not very interesting. It's like you can play the same. You could get tuning forks and you could play with any tune you want on the tuning forks, and it's going to sound hollow because there's basically no harmonics to speak of. So we call this, well, sound quality. And again, my wife is also a French major. So timbre, she says, it's called timbre. I kept saying timbre. She kept saying, no, it's timbre. So she's right. And the interesting thing is, with 2 instruments you've never heard before, the fact you can tell them apart. Because in a way, if you've got 2 synthesizers, how would you know there's 2 synthesizers there? And I believe you can. Sorry? Well, yeah, but if the 512 and the 512 add together and they're synthesizers, it's not even like there's. It's a more difficult test, I think. And I think part of it is, I mean, you've got a single microphone picking up 2 synthesizers, if you like, and you have a single speaker putting it out, and yet you can tell there's 2 of them. And I think it's to do with the phase difference between the 2. I think that one, you know, the chances are that you're going to start your sine wave off at exactly the same time. But I'm suspicious that if you did start your sine wave off at exactly the same time, then you couldn't tell the difference. So that's an experiment that needs to be done. But my wife says I'm wrong, so. But she's right. Okay, I've got to record everything now. So.